said, my name is Sofia Darmaraki. I'm a physical oceanographer from Fourth Research Institute in Greece. I'm very happy to speak with you today and share some of our work. I would like to first thank Chiara and the organizers for inviting me to give this talk today. And now I'm going to go ahead and share my screen. All right, so in this presentation today, I'll try to give you a concise overview of marine heat waves in the Mediterranean Sea, which started as a simple literature review of the latest marine heat wave research in the basin at the time, and resulted in a collaborative study on interdisciplinary aspects of Mediterranean marine heat waves. With the help of many colleagues, some of which are here today, we explored different aspects of this phenomenon in order to provide a well-rounded perspective of surface and subsurface events. So by the end of the talk, I hope we can have some discussions and exchange of ideas on this increasingly important topic. So let's start with what are the marine heat waves, for some of you that may not know. Let's just pretend that this is how the temperature of the ocean looked like some decades ago, where it exceeded the 2 standard deviations only a few times, in which case we were in an extreme warm or cold event. However, the ocean has been warming at an unprecedented rate since the 1980s, as you all know. And this warming, in turn, increases the likelihood of occurrence of extreme warm events, which we now call marine heat waves. You can think of them as equivalent to the atmospheric heat waves, except that these events happen in the ocean, where their effects can be initially hidden from view, but are devastating as some marine ecosystems are no longer able to adapt to the new frequency and intensity of extreme warm temperatures. So why do we investigate marine heat waves in the Mediterranean? This is because this area is a semi-enclosed basin, which has a large marine biodiversity and an active thermohaline circulation. In the last 40 years or so, it has been warming at a rate almost double or more than that of the global ocean, at approximately 0.04 degrees per year. And as a result, the Mediterranean is known as a hotspot region for climate change, which means that by the end of the century and under the business as usual scenario, marine heat waves here are expected to become longer and more intense compared to the past. So to improve our understanding of these events, we compiled a list of marine heat wave studies in the Mediterranean, and I'm going to use the outputs of some of these studies today to give you the outline of marine heat wave story in the Mediterranean. So we begin the review by summarizing the characteristics of past surface and subsurface events, and continue on their local and large-scale drivers, as well as their evolution over time from historical to future projections. The review further explores the documented implications of marine heat waves on Mediterranean marine biota, their effects on socio-economic sectors, and the latest advancements in their monitoring and forecasting. Finally, we highlight key challenges in marine heat wave research, and we then discuss potential avenues for future exploration in the field. To start with, as you can see here in this figure, in this bubble plot, where each bubble represents a marine heat wave, the Mediterranean has experiencing several surface marine heat waves since the 1980s, with various characteristics. For instance, some of the most notable events occurred during the summers of 1999, 2003, 2017, and 2021, lasting between 20 days to 6 months in some cases, and with intensities, so temperature anomalies relative to the climatology, that range locally from 2 to 7 degrees above average. But what is interesting is that almost all studies mostly focus on spring or summer events that display distinct warming signatures in the basin, and consistently report a rising trend in marine heat wave frequency, duration, intensity, and spatial extent. And this is despite variations in methodology, in the use of different data sets, marine heat wave definitions, and periods of examination. Now, this accelerating trend in marine heat wave properties has become more pronounced over the last decades, and It can be explained by a shift in the basin mean SST towards warmer values, most of the times, which, as I said already, increases the likelihood of extreme warm event occurrence. Of course, SST variability has also shown to play a contributing role sometimes. And then a similar increase in the intensity and duration has been also shown for subsurface marine heat waves in the basin, with longer but less frequent events detected at depth. And the vertical extent of these surface marine heat waves can reach up to 300 meters or more, depending on the event. Now, the spatial distribution of surface marine heat wave characteristics reveals a north-south gradient for the mean and maximum marine heat wave intensity, with higher values observed in the northwest Mediterranean Sea, the Adriatic and Aegean Sea, while longer events tend to occur around the Balearic Islands and the Levantine Basin. What is interesting, once again, is that these findings persist regardless of the varying methodology used to detect marine heat waves and the periods of examinations. A higher frequency to the northwest of the basin has been also shown for subsurface marine heat waves, while the longest duration appeared to the southeast of the Mediterranean. However, the vertical extensions of surface marine heat waves, that is, events that start at surface but then propagate in deeper layers, is not consistently distributed in space. For example, some studies show that a lot of events have displayed a progressive eastward subsurface extension, but the summer 2003 marine heat wave, for example, extended deeper in the northwest than in the southeast Mediterranean Sea. And then these marine heat waves are driven by processes that vary in space and time. At the regional scale that you see here, where we can explicitly account for the physical processes governing heat exchange in and out of the mixed layer, most summer events with a surface expression have been linked to increased solar radiation, higher temperatures, persistent low wind speeds, shallower than normal mixed layer depth, and reduced surface heat losses and vertical mixing. However, the influence of atmospheric mechanisms may be overridden by ocean circulation patterns or weather features when we look at a more local scale. For instance, increased temperatures in the North Aegean surface waters during the summer marine heat wave of 2022 were linked to water masses originating from the Black Sea, which occupy the first 50 meters of the water column and induce strong stratification, facilitating further the development of this event. So when analyzing the two major events of the past in the basin, that is the longest record marine heat wave of 2022 and the most intense marine heat wave of 2003, studies show that more or less similar atmospheric conditions, which were linked to high pressure systems, occurred during the formation of these events. However, in the first case, in 2022, hot and humid air masses played a significant role in addition to anticyclonic conditions in the atmosphere, which persisted up to fall season, as opposed to 2003, where cyclonic conditions during fall led to the much earlier dissipation of the marine heat wave. Now, when it comes to subsurface events, their formation depends on the topography, on the season, and especially the winds, which may facilitate the vertical propagation of surface temperature anomalies within a weakly stratified water column. For example, studies agree on a deeper propagation of surface temperature anomalies during autumn compared to summer and spring. And while the local scale drivers of Mediterranean marine heat waves are more or less well studied, their links to large-scale climate modes are poorly understood. For example, current research suggests a connection with the East Atlantic pattern, where the presence of a positive geopotential height anomaly of the 500 hectopascal over the North Atlantic may drive anticyclonic circulation over the Mediterranean, especially towards the west, contributing to the development of these events. Now, one of the increasingly studied topics related to marine heat waves is also their feedback to the atmosphere, and whether marine heat waves occur at the same time with other extreme events. So research so far indicates that over the last 4 decades, marine heat waves in the Mediterranean Sea tend to coincide with atmospheric heat waves, the combination of which can be further related to drought conditions and contribute in turn to wildfire occurrence around the Mediterranean area. Marine heat waves have been also associated to intense storms, such as the Medicane Scott that occurred in the Southeast Mediterranean Sea in October 2019. The Darmaraki supercell formed over the Ionian Sea in November 2012. And during August 2022, in particular, a marine heat wave was shown to amplify a severe storm over the Western Mediterranean Sea and enhance a hailstorm in Spain by providing unprecedented amounts of energy and moisture to the atmosphere. Nevertheless, the impact of marine heat waves on ocean circulation is less explored at the moment. And now that we have an understanding of how marine heat waves have evolved so far, it is important to consider their future evolution. On this graph, you are watching the future evolution of the extreme temperatures in the Mediterranean under different scenarios, the optimistic in green, the intermediate in blue, and the red is the business as usual RCP 8.5. And given that by the end of the 21st century, extreme temperatures in the Mediterranean Sea are expected to rise by up to 4 degrees relative to the past, depending on the greenhouse gas emission scenario, of course, studies consistently indicate an increase in the frequency, duration, spatial extent, and intensity of future surface marine heat waves in the region. And while rising trend in extreme temperature appears independent of the greenhouse gas scenario in the mid-21st century, the influence of the climate change scenario becomes more important towards the end of the century. That is, we are seeing more evidently the differences in how extreme temperatures evolve towards the end of the century. It is interesting that the amplification of marine heat wave is evident across current research, despite, again, differences in climate change scenarios, study periods, identification frameworks, and the type and number of climate models used. In fact, a recent study projects the occurrence of prolonged and intense future marine heat waves with significant impacts on Mediterranean marine protected areas. And this finding holds true regardless of the baseline period against which events are defined, an aspect of marine heat wave study which is currently debated within the research community that I will talk a little bit about in a while. But now, why the study of marine heat waves is important? Well, given that temperature plays a pivotal role in metabolic processes of organisms affecting the growth, fertility, and phenology, this review paper gives an overview of the documented combined effects of the long-term warming trend and marine heat waves on Mediterranean plankton, fish, megafauna, phytoplanktons, and zooplanktons, some of which I am going to cover in the next few slides. So starting here with the most well-studied impacts of marine heat waves. Between 1979 and 2019, over 2,300 mass mortality events have been recorded in the Mediterranean, affecting more than 90 species, with corals being the most impacted, accounting for nearly half of these events, followed by sponges, bryozoans, bivalves, and ascidians. The Western Mediterranean, in fact, appears to be a hotspot, experiencing particularly intense marine heat waves between 1982 and 2017, which were responsible for more than 50% of the recorded mass mortality events. And although mass mortality events usually follow marine heat waves, a direct correlation between the two is actually challenging due to, in part, variation in the sampling effort and study periods, especially because while many species struggle during marine heat waves, some deep sea species found refuge and survived, and in rare cases, non-native reef-forming species have emerged, enhancing species richness and abundance. And as climate change continues to affect the Mediterranean. Rising temperatures and the increasing frequency of marine heat waves are expected to drive substantial changes in other marine ecosystems. For example, marine heat waves have been shown to shift ocean metabolism from a carbon sink to a source and vice versa, while also altering plankton dynamics by favoring smaller phytoplankton, which in turn destabilizes food webs, as well as reducing chlorophyll, which then results in declining primary production, further disrupting the marine environment. And although assessing the effects of marine heat waves on fish population this time is still challenging, evidence suggests that these events actually contribute to biomass declines with cascading effects on fisheries and trophic dynamics. At the same time, thermophilic and invasive species are becoming more prevalent, reshaping ecosystems, with marine heat waves additionally forcing population relocations and reduced egg production. With regard to benthic ecosystems, they are also under severe stress, with declines in Posidonia oceanica, with widespread coral and sponge bleaching, disease outbreaks, and shift in predator populations. Overall, these disruptions give rise to various ecological concerns. The combined effect of long-term and anomalous warming can trigger trophic cascades and biogeochemical shifts, leading to food web instability, while studies show that species resilience varies, with some species adapting and others collapsing. It is important to know that marine heat wave effects interact with multiple other stressors, including pollution, acidification, and overfishing, driving regime shifts, tropicalization, and significant biodiversity loss. This highlights the pressing need for effective management and conservation strategies in the face of intensifying climate stressors. Now, beyond, of course, disruption to ecosystem, a cascading effect of marine heat waves extends to socio-economic ramification on fisheries, aquaculture, and communities that rely on them. Although the available research is currently limited, so far we know that due to distribution shifts and migration or mortality of commercially important fish, the presence of invasive species that damage fishing gear and outcompete native species, and the decline of seagrass meadows, the biodiversity in the Mediterranean coast is changing, directly impacting the catch composition, the abundance, and income of coastal commercial fisheries, with estimated economic losses that can reach up to 700 million euros. Mediterranean aquaculture is also highly vulnerable, as farmed species cannot escape rising temperatures, and then marine heat waves can cause hypoxia, leading to mass fish die-offs. In fact, future projections suggest, in a recent study, that marine heat wave-induced losses in fish farms could reach up to 10 million euros. For example, here you can see bivalve farming has already suffered, with mussel production experiencing up to 90 to 100% mortality during an extreme event, severely impacting, of course, local economies and supply chains. And last but not least is the effect of marine heat waves on reducing the recreational and aesthetic value of coralligenous areas, with, again, significant welfare losses. And while marine heat wave impacts in the Mediterranean are well documented, their assessments remains challenging due to limited observational coverage across spatial and temporal scales. Given that organisms and ecosystems respond differently to marine heat wave, they require targeted monitoring approaches, with recent advancements including multi-platform studies integrating in situ with satellite data to analyze ecosystem responses. Forecasting efforts also show promise, with short-term predictions successfully capturing marine heat waves, and seasonal forecasting still requiring refinement. Meanwhile, machine learning emerged as another powerful tool for marine heat wave prediction, often enhancing computational efficiency and outperforming traditional models in predicting SST anomalies and marine heat waves. Now let's go to some challenges in the marine heat wave study, and some of the most controversial aspects of these events are the challenges in defining and detecting marine heat waves. For example, at the moment, there is a versatile framework proposed by Hopday et al. 2016 that has been widely used so far, whereby a marine heat wave occurs when the daily temperature exceeds a local seasonally varying 90th percentile temperature threshold for at least 5 days. However, variations of this definition exist and include different temperature extreme thresholds, different baseline periods, different gap days, minimum duration and spatial extent, and so on. Overall, detecting a balanced number of marine heat waves over a specific period of examination using a statistical identification framework needs careful tuning of the spatiotemporal parameters, and each approach has actually its merits and disadvantages. For example, the question of using a fixed or a moving baseline to detect marine heat waves in the future serves different purposes. In the first case, it leads to marine heat wave saturation in the future, but effectively communicate the effects of long-term warming, whereas the choice of the shifted baseline captures more recent extreme events, but kind of masks climate change effects. Either way, the choice depends on the specific research question. And limitations, of course, also exist in the assessment of physical drivers behind marine heat waves, since atmospheric processes tend to become more important than oceanic circulation processes in driving these events as the spatial extent of the events becomes larger. In addition, the duration of marine heat wave onset and decline affects the dominant driver diagnosed in each phase, especially in prolonged events, while the selected integration depth or the extent of the mixed layer depth considered also has an effect on the dominant drivers diagnosed, especially behind subsurface marine heat waves. And that is why future research on Mediterranean marine heat waves necessitates a lot of changes and improvement of subsurface observational systems using biogeochemical Argo floats, gliders, and moorings, alongside high-resolution models and real-time remote sensing. Machine learning approaches, of course, also show a promise by integrating physical laws into machine learning frameworks, which could enhance prediction reliability. Yet, challenges remain in balancing computational costs and physical constraints. Additionally, marine heat wave research should expand beyond summer events in the Mediterranean to assess seasonal variability, feedback with the atmosphere, links to large-scale climate modes, and understanding the ecological impacts of marine heat waves on marine biodiversity, particularly within marine protected areas, is essential for developing climate-based conservation strategies. While more studies are needed to assess the socio-economic impacts of these events in the basin, as well as their effects on the biogeochemistry of the Mediterranean. And at this point, I would like to acknowledge all of my colleagues without whom this collaborative study would not have been possible. And I would like to thank them officially. And I would like to thank all of you for your attention. And finally, I would like at this point to just say that I'm also interested to work in the development of marine heat waves in polar oceans, and thus I am looking for collaborations or projects or people that would be interested to work in this kind of topic in case anyone in the audience is aware of any such opportunities. So thank you very much. I'll take question.